Imagine you're standing at the edge of the observable universe, watching the very last stars flicker out one by one. It's 100 trillion years in the future, and reality itself is grinding to a halt. The sky, once filled with infinite light and possibility, has become an endless void of darkness. Somewhere in this dying cosmos, the remnants of a civilization that once commanded entire star systems now huddles together, not in grand towers and marble and steel, but inside a thin shell wrapped around a black hole. They've reached the end of all things, and all they can do is watch the universe die. But here's the thing, they're not helpless. They've bent the rules of existence itself. They've slowed time so drastically that while trillions of years pass outside, only moments tick by for them. They're seeing the future unfold in real time, watching the universe's death throes like a slow-motion film. And the secret to their survival? A concept so fundamental, so woven into the fabric of reality, that without it, you wouldn't exist, time wouldn't flow, and the universe itself would be unrecognizable. That secret is buried in the nature of space and time itself. Now, before we dive into this cosmic mystery, if you're genuinely interested in understanding how the universe works, how reality bends, stretches, and transforms, you'll want to stick around. And if you find this genuinely useful, hit that subscribe button so you don't miss future deep dives into the mysteries of existence. Trust me, what's coming will blow your mind. Welcome to Beyond the Stars, the mysteries of existence. Trust me, what's coming will blow your mind. Let's start with a simple question. What is space? Really, think about it. As kids, we learn that the world around us has 3 dimensions, up and down, left and right, forward and backward. We're free to move through all of them. Space is just there, the invisible stage where everything happens. But for thousands of years, philosophers and scientists have been bothered by this. Plato called it the nurse of becoming. Aristotle insisted that empty space couldn't possibly exist, but they were wrestling with something that seemed too obvious to question. It wasn't until the 1600s that a man named Galileo started thinking about a weird thought experiment. Picture a sailor locked in a cabin below deck on a ship, no windows. Just a table with plates, knives, and a goldfish in a bowl. Some birds and insects flutter around. The ship is docked in port, so everything is calm and peaceful. The fish swims happily. The plates stay on the table. Everything is normal. But then, the ship sets sail and hits rough waters. Suddenly, the cabin heaves and falls. Plates go flying. Water splashes from the bowl. But here's where it gets interesting. When the sea calms down and the ship cruises smoothly across glassy water, everything inside the cabin goes back to normal. The plates stop moving. The fish swims peacefully again. The sailor sits comfortably. And from his perspective, it's exactly like being docked in port again. Now, without looking out a window, the sailor has no way of knowing whether he's moving or standing still. He could do any experiment he wanted, drop a ball, light a candle, measure anything, and he'd get the same results whether the ship was stationary or sailing at full speed. Galileo realized something revolutionary. Motion is relative. There's no such thing as absolute stillness. You can only measure motion compared to something else. This became the first theory of relativity, and it's still true today. Fast forward to the late 1600s, and 2 of history's greatest minds were about to have a massive argument about what space actually is. Isaac Newton, born the same year Galileo died, declared that space was something absolute. It existed independently, a rigid stage where all motion played out. Space, Newton said, would exist even if the entire universe was empty, no matter what. His opponent was Gottfried Leibniz, a brilliant mathematician who disagreed completely. Leibniz argued that space only had meaning in relation to objects. Without things to measure distances between, space itself would be meaningless. The argument raged for years. Newton won that battle, and his absolute space dominated science for nearly 200 years. But here's the catch. Even Newton accepted Galileo's idea that absolute rest didn't exist. Space was absolute, but you could never prove you weren't moving. Then came time. And Newton had very different ideas about this. Time, he declared, flowed absolutely and uniformly everywhere in the universe. A second on Earth was the same as a second on the most distant star. Universal synchronicity. Every clock, everywhere, ticked to the same cosmic beat. But was Newton right? Is time really that simple? That's where things get wild. Let's talk about heat for a moment. Sounds random, but stay with me. When the Industrial Revolution arrived, engineers faced a practical problem. A horse could work all day if you fed it enough hay. But how do you measure how much work you can extract from coal? This question led to an entire field of study, thermodynamics. And thermodynamics revealed something disturbing about the universe itself. Energy isn't used up cleanly, it's always wasted as heat. A steam engine burning coal might only be 3% efficient. Most of that energy just radiates away. It's impossible to build a perfectly efficient machine because energy always degrades from concentrated to dispersed form. Physicists introduced a new concept to measure this: entropy. It's essentially a measure of disorder. And here's the terrifying part: entropy always increases. Always. The universe is constantly becoming more disordered, more chaotic, more degraded. Lord Kelvin looked at this and concluded something dark. The universe is dying. It's heading toward heat death. A state where all useful energy is exhausted. Everything is the same temperature, and nothing can change anymore. The cosmos is slowly winding down, running out of steam, approaching eternal darkness. But entropy revealed something else. Something about time itself. You see, entropy only increases in one direction. You can unscramble an egg from a cracked state back to whole, but you'll never see a broken egg on the floor spontaneously reassemble and jump back onto the table. Coffee cools down. It never spontaneously heats up. Fires burn, but you never see ash and smoke spontaneously transform back into wood. This is the arrow of time. Entropy gives time a direction, and that direction is the only reason you can distinguish yesterday from tomorrow. Now we get to Einstein. At the turn of the 20th century, physics had a serious problem. Light always traveled at the same speed, about 300,000 kilometers per second, regardless of the observer's motion. But Newton's laws said that speeds should add together. If you're standing on a train moving at 100 kilometers per hour and throw a ball forward at 50 kilometers per hour, someone on the ground sees the ball moving at 150 kilometers per hour. Simple arithmetic. But light doesn't work that way. Light always travels at light speed, no matter who's measuring it or how fast they're moving. This broke everything Newton had built. Einstein made a radical proposal. Light speed is constant, but space and time are not. He declared that every observer has their own measurement of space and time. Space isn't absolute. Time isn't universal. They're relative. They change depending on who's measuring and how they're moving. This was his special theory of relativity, and it rewrote physics completely. But Einstein wasn't done. A few years later, he asked the biggest question: what about gravity? And the answer he found changed everything. Gravity, Einstein realized, isn't actually a force pulling you down. It's something far stranger. Massive objects bend and curve space and time around themselves. You're not being pulled to Earth. You're actually moving in a straight line through curved spacetime. The Earth's mass warps the fabric of reality around it, and you're just following the contours. Space and time aren't a rigid stage. They're dynamic, flexible, alive. They bend, stretch, curve, and ripple. Near a black hole, this curvature becomes extreme. Time itself slows down. Clocks near the event horizon tick much slower than clocks far away in empty space. This is why that future civilization built their home around a black hole. In the intense gravitational field, time moves slower. Trillions of years pass in the outside universe, while only moments pass for them. They've essentially bought themselves time, literally, by exploiting the very nature of spacetime itself. But as our dying civilization watched the universe collapse around them, they realized something terrifying. There's another layer to reality, one even more fundamental: quantum mechanics. At the smallest scales, reality behaves completely differently. Particles can exist in multiple places simultaneously. They can tunnel through barriers. The universe is fundamentally probabilistic, not deterministic. And when physicists tried to merge quantum mechanics with Einstein's relativity, everything broke. The equations produced infinities. Nothing worked. For over a century, we've struggled to unify these two pillars of physics. Some think space and time might be emergent phenomena, that at the tiniest scales, below what we can observe, space and time don't really exist at all. Instead, there might be something more fundamental underneath. Quantum grains of spacetime, fundamental bits of reality and their relationships. At our scale, these combine to create the illusion of smooth, continuous space and time. But at the deepest level, they might be pixelated, granular, chunky. The truth is, we don't know. And maybe we never will. What we do know is that space and time, these things that seem so obvious and everyday, hide mysteries that we're only beginning to understand. Einstein transformed our understanding forever. But the universe still has secrets, the biggest ones. So here's my question for you. Aren't you curious about what else we don't understand about reality? About the actual structure of existence? Because the more we learn, the stranger the universe becomes. If you want to explore these mysteries with me, subscribe to the channel. Join a community of people fascinated by the deepest questions humanity can ask.